All right, let's talk about reaction rates, also known as kinetics. Okay, the meaning of reaction rate. Let's go over this. So, reaction rate can be symbolized with R, and that is the change in something over the change in time. And in chemistry, the something could be products or reactants. All right, let's first talk about collision theory so that this all makes sense. So, in order for a reaction to occur, first of all, there must be a meaningful collision between particles. And a meaningful collision must involve two things. First, that it has the correct orientation, and secondly, that it has enough energy. Okay, let's continue with collision theory. It says that it must collide with enough energy and the correct orientation. Those are the two things that we just talked about. Let's look at these four possibilities. We have a reaction with carbon, nitrogen, and oxygen here. And you can see that there are some situations in which these elements can come together. In this first one, in A, we have the incorrect orientation. So there is a collision, but they rebound because they're not in the correct orientation or they're not facing the right direction. In part B here, this is also the incorrect orientation, but notice how these two are different, okay? So this first one we have two oxygens coming together, and this one we have an oxygen and a nitrogen coming together, and it will result in a rebound. Okay, let's move on to D. All right, so we have a collision, and it looks like carbon and oxygen are here together, and they do collide. But if there's not enough energy presented in this situation, they will also result in a rebound. But let's look at C here. This is the one where it does actually end up working. So there's a collision with carbon and oxygen, nitrogen, and oxygen here. So this is the correct orientation for carbon and oxygen to come together, and it forms what is known as the activated complex. This is a moment, a very fleeting moment, where this compound is formed. Okay, so it's sort of stuck together, and then the rebound occurs, but you create two products that are new from the reactants. In this case, we have carbon dioxide here, and we have nitrogen monoxide, which are both different from the initial reactants. Okay, so it does have to have enough energy to form this activated complex, and then it also has to have the correct orientation. All right, let's look at an energy diagram that represents this process. Along the y-axis, we have energy, and on the x-axis, we have the reaction progress. That could also be seen as time. Okay, so we have our reactants here, and they have some energy on the y-axis. And then we have our products, which have a lower energy down here. Okay, here's our activated complex up here. This difference right here is known as the activation energy. That's the energy that is required to produce the activated complex. You have to have sufficient energy to make this. And then this difference down here is the energy released by the reaction. That is the difference between the reactants, and the products. Okay. I like to look at this as a hill. So if you don't have enough energy to push, let's say, a boulder up a hill, you're never going to get it all the way down the hill over here, right? You have to have enough energy to get it up, and then it will do the rest for you. Okay, so just take a moment to look at this diagram. It's an important one for you to understand. Factors that affect the reaction rate are the following four: temperature, concentration, particle size, and catalysts. You do need to know those four. Let's start with temperature. So recall that temperature is a measure of kinetic energy. Hopefully you've learned this before, maybe in a different science class, but what kinetic energy is 1/2 mv squared. That is how you measure it. So it's 1/2 the mass times the velocity, and the velocity part is squared here. Okay, so even though compounds typically have very little mass, they're traveling extremely fast. And when it's squared, and then you multiply it by this coefficient of 1/2, you end up with the kinetic energy. And it just so happens that the average kinetic energy of a substance is its temperature. Okay. The faster something is moving, the more likely it is to collide with other particles, which should make sense, and we've all experienced this before. It's the reason that we use hot water to wash our dishes. As the particles are moving around really fast, they run into things more often and with more force. They have a higher kinetic energy. Whereas something that's moving along really slowly doesn't have as much potential to run into other things, and it doesn't have as much energy. So that's why we wash our dishes with hot water. Okay, the second one is concentration. Higher concentrations of particles increases the likelihood of interactions. So let's look at one that we've seen before. Here's capital M again, that is molarity, moles of solute over liters of solution. If we compare two solutions that are mixed together, let's say we have a 0.5 molar solution of this green and a 1 molar solution here, and then we double each of these, and we have 1 molar and 2 molar, you can clearly see that this one on the right, there's going to be more particles in solution, and it's going to be more likely that they interact together. It's kind of like in the hallway. If there's more people in the hallway, there's more likelihood for interactions with each other. Pretty straightforward. Okay, particle size as well. So increased surface area provides more opportunity for reactions to take place. This is a good example that I like to use. Which would you start with to create fire? Would you start with little tiny pieces like kindling, or tiny sticks, or a giant log? Well, if you've ever been camping before, you know you definitely start with kindling because there's more surface area, there's more gaps between the splinters of wood for oxygen to get in and to fuel the fire, right? And then you can progress and move on to bigger ones and sustain this combustion reaction. And lastly, catalysts. Catalysts are never consumed during a chemical reaction, they simply facilitate. Catalysts are compounds within chemical reactions, okay, that are not consumed during the reaction, they just sort of help to overcome the activation energy. So remember the hill that we looked at earlier. So if you have a hill that you need to overcome, a catalyst can facilitate the reaction or help it proceed and lowers the activation energy. It basically makes the hill smaller. Enzymes are a good example of a catalyst. Enzymes in our gut facilitate the digestion of food, whereas if we didn't have these enzymes, then it would take a lot longer for our food to digest. Okay, and this works for when reactants are higher in energy than products, and the reverse, where reactants are lower in energy than the products. Either way, if we're going this way, it reduces the activation energy. Okay, go ahead and test yourself by completing this diagram here. So I want you to list A through E, answer whether it's exothermic or endothermic, and draw what a catalyst would do. And also label these two axes. Go ahead and pause the video and give this a try. Okay, so hopefully you gave that a go. Let's talk about the answers here. On the y-axis, we have energy, and on the x-axis, we have the reaction progress. A would be for this, where it goes from left to right. A would be the reactants. B is the activated complex, that sort of fleeting combination of reactants before they break apart into products. And of course, C would be where the products are. D would be the energy released by the reaction. That's the difference between the energy of A and the energy of C, the reactants and products. E is the activation energy right here. Okay, that's the amount of energy required to make the activated complex. And a catalyst is shown here in pink. What it would do is reduce that activation energy to something that's easier to overcome. Okay. Also, this is an exothermic reaction because energy is released in this process. If you have more energy with your reactants and less energy with the products, the difference, the energy released, D here, has to go somewhere, and it is released by this reaction. Okay, if this were the opposite, let's say that we flip this and we go this way, this would be an endothermic reaction, and the activation energy would be much larger. Okay, so just think about this diagram. Let me know if you have any questions about this. I'm happy to help, and I'll see you next time.